Let us start lecture 47, and the course is on phase diagrams in single component and binary systems. And today's topic we will discuss enthalpy of mixing, what we have the expression what we have realized in the last lecture, considering regular solution model, and then accordingly we will also see how Gibbs free energy of mixing varies due to the non-zero value of del H mix in case of non-ideal system. Now, what we have discussed in the last lecture, we have found out an expression for del H mix, and we have done it for binary system. So, binary solution. Of course, we have considered two metals A and B. We have taken Na number of atoms and Nb number of atoms of A and B. This is number of atoms, and when you add them together, if you add them together, it yields me Avogadro number. Number of atoms. So, we are considering 1 mole of solution and their mole fractions are Xa and Xb. Both of them have same crystal structure. Same crystal structure. So, that means the coordination number, which is Z, is also same. In fact, in the solution also, so that is also having the same crystal structure. We are considering at a particular temperature and pressure, we are taking pressure to be 1 atmosphere. We have framed this particular del H mix, which is nothing but omega Xa and Xb, where omega is nothing but Avogadro number, coordination number, and a difference of bond energies of AB, that means dissimilar atom bond, and similar type of bonds AA and BB type. So, that difference was reflected like this. Fine, and it is done on the framework of, this is done on the framework of regular solution model. Fine, and we have also seen if this value is positive, then definitely the like atoms would like to have bonds. If this del H mix value is negative, dissimilar atoms will have the tendency to form bonds, and accordingly we can get phase separation, we can get compound formation, we can get clustering, we can get short range order, those kind of things we have already discussed. Now, we will treat this particular del H mix. Now, if I try to look at this energy part, we can see that del H mix is 0 when equal to by 2. Fine. And in fact, if you recall Raoult's law, so that time we have considered the bond energy of all types of bond are equal. In fact, this is also reflected here. Okay. So, that is what when del H mix equal to 0, it becomes ideal. So, this is ideal solution case. Fine. An ideal case, we can express delta G mix equal to del H mix, this is a generic equation, minus T del S mix, and here since this is 0, So, I can write delta G ideal and I can also write del S mix ideal. We will see why I am writing this ideal. So, delta G mix ideal equal to minus T del S mix ideal. Okay. So, in case of ideal solution, this applies. This applies. But when it becomes non-ideal, that time this simple equation will not hold. We have to consider del H mix. So, let us consider a non-ideal case. Non-ideal solution. So, in case of non-ideal solution, I can write delta G mix equal to del H mix minus T del S mix. This can be written. So, now I can write delta G mix equal to X A X B minus T del S mix. Now, we have taken one major assumption in case of regular solution model. One assumption was del S mix is nothing but minus R X A ln X A plus X B ln X B, which is coming due to configurational contribution. But other terms, like for example, there could be a vibrational entropy also. Vibrational entropy also, but that is neglected or ignored. So, we can take it as 0 for regular solution case. So, that means whether we are taking regular solution or ideal solution, both the cases del S, we could see that since regular solution model does not consider vibrational entropy term, it only consider configurational entropy term. So, then I can say that del S mix ideal is nothing but del S mix. So, the del S mix in case of regular. Okay. So, we can write this as delta G mix ideal equal to R T X A ln X A plus X B ln X B. Okay. Similarly, here I can write delta G mix equal to X A X B plus R T X A ln X A plus X B ln X B. We have to find out what is the solution free energy once we have the solution in case of ideal as well as in case of non-ideal case. So, in case of ideal, let me treat first ideal solution. So, ideal solution case G2 ideal equal to G1 ideal plus delta G mix. So, it can be written as X A G A naught plus X B G B naught. So, G A naught and G B naught are basically molar free energy for A and B when they are in their pure condition. Now, we have taken 1 atmosphere. So, that is what these value becomes standard values. We have put a superscript 0 value, okay, 0 mark. Now, remember all the treatments are basically with respect to 1 mole of substance. So, whatever you see here, it is always 1 mole. For example, this is 1 mole, this is when we combine these two terms X A G A naught and X B G B naught, that those are also for 1 mole substance. So, together it becomes 1 mole, and this term, the delta G mix, is also for 1 mole. because we are forming 1 mole of substance, 1 mole of solution. Plus we write RT XA ln XA plus XB ln XB. So this can be written as XA GA naught plus RT ln XA plus XB GB naught plus RT ln XB. So this is G2 ideal. So now we can write this one as G2 ideal equal to XA GA bar plus XB GB bar. So this GA bar and GB bar are basically partial molar free energy of A and B in the solution. Okay. So these are partial quantities. We can say molar partial Gibbs free energy or chemical potential of A and B in the solution. Fine. So GA bar equal to GA naught plus RT ln XA and GB bar equal to GB naught plus RT ln XB. So let me treat a non-ideal case. Non-ideal case, G2 ideal equal to G1, not ideal, G2, G1, and remember G1 is basically unmixed condition. So here this is nothing but unmixed pure condition. So here also G1 is unmixed pure condition. So that means that expression for G1 in case of ideal or non-ideal, that would remain same. So plus delta Gmix non-ideal. So now we can write G2 equal to XA GA naught plus XB GB naught plus XP plus RT XA ln XA plus XP ln XP. Now we can do some smart processing of this particular equation. XA GA naught plus XP GB naught plus, so this term we can actually multiply with 1, okay, and that 1 can be written as XA plus XP, because XA plus XP is nothing but 1 in the solution. So then I can write XA plus XB XA XB plus RT XA ln XA plus XP ln XB. We can separate out all the terms with XA term and XP term. So XA GA naught, we can put it like this: XA XB square plus RT ln XA XA plus XB GB naught plus XA square XB plus XP RT ln XP. So this becomes XA GA naught plus XP square plus RT ln XA plus XB GB naught plus omega x a square plus RT ln xb. So, G2 can be also written as XA GA bar plus XB GB bar. Then I can write GA bar equal to GA naught plus omega, and instead of XB I can write 1 minus XA square, because XA plus XB equal to 1. So, XA would be equal to 1 minus XB and XB equal to 1 minus XA. So, I can apply this into this equation. So, then plus RT ln XA and GB bar equal to GB naught plus omega 1 minus XB square plus RT ln XB. Fine. So, we are getting two equations for the partial molar Gibbs free energy of A and B in the solution. Okay. So, we could see that two partial quantities or chemical potential are expressed differently in case of ideal or in case of non-ideal situations. I missed a term here. When we treated ideal solution, please put this delta G mix should be also ideal. Okay. Now, once we get this, so we could see that in case of ideal case, we express those chemical potentials differently than in case of non-ideal case. Now, that means when we talk about ideal as well as non-ideal, considering a regular solution model is active there. So, there would be some, in order to distinguish regular solution and ideal solution, there could be, that could be done with the help of excess function. In fact, if we see that G2 when it is ideal and when it is not ideal, non-ideal, so that means there could be difference between these two, and that difference should be the excess function, because the Gibbs free energy is an extensive quantity. Okay. So, we can now make a difference of regular solution model and ideal solution. So, we can write G2 for non-ideal case should be equal to G2 ideal plus G excess. So, this is G excess is nothing but excess free energy, which is the difference between the free energies of solution when it is non-ideal and another case when it is ideal, and here the non-ideal treatment is based on regular solution model. So, we can actually get a relation between G excess and enthalpy of mixing, what we have found out. So, G2 in this case is nothing but G1 plus T1 plus delta Gmix equal to G2 G1 plus delta Gmix ideal plus G excess. It can be written as G1 plus del H mix minus T del S mix equal to G1 plus del H mix, which is 0 in case of ideal, minus T del S mix ideal plus G excess. So, we could see that this both the cases, this G1 is same because this is unmixed condition. So, we have also seen that these two are same because we are not considering any vibrational entropy term only mixing entropy term, which is coming due to configurational entropy. So, Gxs is nothing but delta Hmix, which is nothing but Xa Xp. So, then Gxs can be also written as Hxs minus T Sxs. Since this Sxs is also 0, because we do not get any excess entropy when the solution is formed ideally or non-ideally. So, this is 0. So, if that is 0, then we can actually see that this omega should be a constant term. So, now we can see that from here we can also get an equation delta G xs delta T constant pressure and composition should be equal to minus S xs. Fine. So, once we get that, so since we are considering this is to be 0, so this is 0. So, that means G xs is temperature independent term. Now, this is equal to omega Xa Xp. So, Xa Xp are those compositions. So, then this must be also temperature independent term. Okay. In fact, if you see this omega expression, which is nothing but Avogadro number Z, which is this is E is the difference, E is nothing but epsilon E is nothing but EAB minus EAA plus EBB by 2. Okay. So, now here you see this potential energies, they do not vary much with the temperature. So, they remain constant, because we can say that those are basically internal energies. Okay. So, now these two term is a constant, this is also a constant, Z and Avogadro number. Okay. So, this term should be a constant term. Now, once we know that omega is a constant, so now we can actually go and treat our expression for partial molar Gibbs free energy or the chemical potential. In case of a general formula for in terms of activity, if we write that G2 can be written as Xa Ga bar plus Xb Gb bar, where we can write Ga bar equal to Ga naught plus RT ln Aa, and Gb bar would be equal to Gb naught plus RT ln Ab. Okay. So, we can write that. Now, in case of ideal solution, we have seen that Ga bar equal to Ga naught plus RT ln Xa, this one. So, we can write, if I combine this and this, if I compare, so I can write RT ln Xa should be equal to RT ln Aa. So, from that we can say that Xa. So, we can say that Aa divided by Xa is equal to 1, and we know that A I equal to gamma I Xi. Gamma I is nothing but activity coefficient. So, we can say that gamma I should be 1, or gamma A here should be 1, and similar way we can prove gamma B should be 1, by comparing. So, we from here we can write gamma A equal to 1. Now, another comparison we can do GB bar equal to GB naught plus RT ln XB. So, again we can compare with this equation with this. So, we can get RT ln XB equal to RT ln AB. So, this is at a particular temperature, the R is a gas constant. So, AB by XB should be 1. Okay. So, it gives you gamma B is equal to 1. Fine. So, that is the ideal consideration. Now, let us treat non-ideal cases. Non-ideal cases we can compare, for example, GA bar equal to GA naught plus and GB bar equal to GB naught plus omega 1 minus XB square plus RT ln XB. Okay. So, then we can write by comparing the first one. Let us say this is equation 1, this is equation 2. So, equation 1 and this is equation 3 and equation 4. 1 and 3 if we compare, we can say that A RT ln AA should be equal to omega 1 minus XA square plus RT ln XA. So, we can write RT AA divided by XA equal to omega 1 minus XA square. There should be ln term. Please, I have missed this ln term. So, ln divided by RT. So, we can write gamma ln gamma A equal to omega 1 minus XA square divided RT. Fine. So, we can get this equation, or we can write in this way gamma A equal to exponential omega 1 minus XA square by RT. Fine. So, we get one equation like this. So, another equation we can get by comparing 2 and 3, 2 and 4. So, we can write RT ln AB equal to omega 1 minus XB square plus RT ln XB. So, we can write AB divided by XB equal to gamma B equal to exponential omega 1 minus XB square divided by RT. So, we are getting the equation 5 and equation 6, let us say. Now, let us see the equation 5. If we take equation 5. So, now if I consider XB tends to 0. So, that means very dilute solution of B in E. B in A. Okay. So, that time, so then X A tends to 1. So, if I write that, then gamma A should be equal to exponential omega 1 minus 1 divided by RT. Okay. So, then equal to 1. But if I take equation 6, then xb the same consideration, omega gamma b equal to exponential omega 1 minus xb divided by RT square. Of course, there is a square term. So, that should be equal to exponential omega by RT. Okay. Now, we see that at a particular temperature and pressure, omega is a constant, R and T both are constant. So, that means gamma b is a constant term. Okay. So, I can write A b divided by x b equal to gamma b, which is a constant. So, then it becomes A b equal to gamma b x b. So, here this is nothing but Henry's law. Similarly, on the other side, if we start, this is case 1. So, let us take case 2, where we take equation 5. So, that is nothing but gamma a equal to exponential omega 1 minus x a square divided by R t. So, now in this case we are considering x a tends to 0 and x b tends to 1. It means we are taking very dilute solution of A in B. So, once we do that, this gives me gamma A should, because it is coming out to be exponential omega R t is nothing but a constant. We can write A equal to gamma A x a, which is the statement of Henry's law. Fine. Now, if I take equation 6, exponential equation 6, gamma b equal to exponential omega 1 minus x b square divided by R t. So, this becomes, with this consideration, gamma b becomes 1. So, what does it mean? So, in case of the case, this is case 2. Okay. So, in case of case 1, when x b tends to 0, the solute B follows Henry's law in the solution of A b. So, the solute B follows Henry's law in the solution of, or rather I would say dilute solution, very dilute solution of B in A. If we see this gamma A equal to 1, it means that the solvent will follow Raoult's law. Okay. In this case, the other case, when we are talking about this, so it is just other way around. The solute A follows Henry's law in a very dilute solution of A in B. Okay. But when we talk about this one, solvent B, we can write solvent B follows Raoult's law. Now, so we can understand two things, that when you consider a solution of A and B, and if we take a very dilute solution, the solvent would follow Raoult's law or ideality, whereas the solute would follow Henry's law or the non-ideality. Okay. So, we will stop here, we will continue the same discussion in our next lecture, and there we will try to relate this particular information what we have snatched right now with the help of this equation. We can take it in the graphical mode, and at the same time now we will slowly go and try to see how del Hmix varies, whether it goes to a small positive, small negative, or large positive, large negative, and on the and when it goes like that, then what will be the effect on the Gibbs free energy for mixing of A and B, that means the solution Gibbs free energy or the mixing solution free energy, and subsequently it will also change the solution free energy too. Okay. So, we will stop now, we will continue the same discussion in our next lecture. Thank you.